Hello, everyone. So we're going to be covering the October-November 2023. This is variant 2, IGCSE Physics, paper 4. So question 1 says, a car accelerates uniformly, meaning constant acceleration, in a straight line from rest at time t equals 0. And then at time 3.2 seconds, so 3.2 seconds later, the speed of the car is 13 meters per second. Calculate the acceleration. So there's two equations for acceleration. One involves F equals ma, but in this question, they haven't given you the force, they haven't given you the mass. So you're not going to be using this equation. We use the other equation for acceleration, which is the change in velocity over time, which is v minus u over t. Now, v is the final speed, which is 13 meters per second. That was the final speed of the car. Use the initial speed, and it says it accelerates from rest. Rest meaning the initial speed was 0, so v minus 0. Over the time, or how long did it took? Well, we went from t equals 0 to t equals 3.2, so it took 3.2 seconds. So you're going to say acceleration in this case would be 13 over the time, which is 3.2. If you put this in your calculator, you will get 4.0625. 4.0625. But we're going to round two significant figures just because the time was given in two significant figures. So we're going to round to 4.1 equals 4.1 meters per second squared, which is the unit for acceleration. Okay, now it says, explain in words what is meant by the term acceleration. Well, acceleration is defined as acceleration is the rate of change of velocity. Now, every time you see the word rate, that just means divided by time, right? So in this context, it will be change in velocity over time, right? That's what rate of change of velocity means. Now it says the car travels at 13 meters per second from t equals 3.2 to 12 seconds. Plot the speed time graph for the car from 0 to 12 seconds. Well, first we're going to plot the graph from 0 to 3.2 seconds. And we know that from 0 to 3.2 seconds, the car was accelerating uniformly, as it told us in part A. And it was accelerating uniformly, acceleration of 4.1. And we know that the initial speed was 0 and the final speed was 13. So our initial speed was 0 and our final speed was 13. So 13's in between 12 and 14, so around here. Okay, and we know it took 3.2 seconds. Well, the question is, how do I know where 3.2 seconds is on the x-axis? Well, what you can do is you look at what the difference is between these two. Well, the difference between 2 and 4, for example, is 2. And then you count how many squares there are between them. Well, there's 1, 2, 3, 4, 5 squares. So what you do now is you do the difference over the number of squares. And this gives me 0.4. So that means each little square is worth 0.4. Okay, so if each little square is worth 0.4, this will be 2.4, this will be 2.8, and then finally this will be 3.2. And I know that 3.2 seconds later, my speed was 13. So if I just go up here, and then I'm going to mark the point X over here. So at time t equals 0 seconds, your speed was 0. And at time t is equal to 3.2 seconds, your speed was 13. Okay, so now I've drew the graph from 0 to 3.2. But now I want to draw it from 3.2 to 12 seconds. So I'll get the full sketch. So from 3.2 to 12 seconds, the car was traveling at a constant speed of 13 meters per second. So how would it look like if I just use this? Let's normally sketch the speed time from 0 to 3.2. It will just look like this. And then from 3.2 to 12, so here's 12, by the way. So from 3.2 to 12, it was just a straight line. That's not good, actually. There you go. So I have to make sure that my line is right in the middle because 13 meters per second is in the middle. Okay, so yeah, this is my sketch. Obviously, you want to sketch with a pencil. Determine the distance traveled by the car from 0 to 3.2 seconds. Well, the distance traveled, by the way, is always the area under the graph. And we kind of drew the graph already. It looked like this. This was the graph. So we're going to want the area under the graph. Well, here we have a triangle. And the area of a triangle is the base, where the base is 3.2 multiplied by the height, or the height is 13 divided by 2, right? So what we're going to write here and we're working out is we're going to say the distance traveled, the area under the graph, and then I'm going to write, which is triangle, right? So area of a triangle, base times height divided by 2. It's important you show the examiner you're working out, otherwise you might lose the working out mark. And then in this case, the base was 3.2 times the height, which was 13. So 3.2 times by 13, and then divided by 2. And that would give you that would give you 21 meters if you round to two significant figures. So therefore, that will be equal to 21 meters. Do not forget the unit. All right, let's carry on. The car decelerates from 13 meters per second to 0 meters per second at a constant deceleration. The mass of the car is 1350 kilograms. The car travels 13 meters in 2 seconds as it decelerates. Show that the work done by the car as it decelerates is 1.1 times 10 to 5 joules. Well, the equation for work done is force times distance. Remember, work done is the energy transferred, but when it's giving you the distance, you want to use force times distance. Okay, we know the distance is 13 meters. It travels 13 meters. So we can say D is equal to 13 meters. Now the question is, what is the force? Well, there's several equations for force, and the relevant one here will be mass times acceleration because it's giving you the mass, and it's also allowed you to work out acceleration. So we're going to say that the force in this case is mass times acceleration. And then we're going to say that the acceleration is just the change in velocity over the time. Now, the change in velocity is 13 meters per second because you went from 13 to 0. So that's the change in your velocity. And it took 2 seconds this time. So your time will be 2 seconds. This gives me, what, 6.5 meters per second squared. All right, so now we know the acceleration. We also know the mass. We could work out the force. We could say the force is the mass, which is 1350, times by the acceleration, which is 6.5. This gives me 8775 newtons, so 8775 newtons. So now we know the force and we know the distance. We could use this equation now. We could say 8775 times the distance, which is 13. This gives me 114,075 joules, which if you round and put it in standard form, it becomes 1.1, right? Because 4 rounds to 1. So 1.1 times 10 to the 1, 2, 3, 4, 5, sometimes 10 to 5 joules. All right, let's carry on. On another day, the car travels a longer distance while it decelerates from 13 meters per second to 0 meters per second. The deceleration is constant. So just to explain what causes the stopping distance to increase. Well, what causes stopping distance to increase is we have to think about what the factors impacting stopping distance. It could be the mass of the car. So if you have a larger mass, of a car, then it's going to, if you use the equation F equals ma, and we rearrange to make acceleration the subject. We know that acceleration is equal to the force acting on the car, which will be the force by the brakes. It's the frictional force divided by the mass. And I want you to keep in mind that if you have a smaller acceleration, it's going to take longer for the car to stop, because we know that acceleration is your change in velocity over time. And if we make the time the subject, we just swap these two around. So we could say time is equal to change in velocity over acceleration. Now, the change in velocity is constant because you are traveling from 13 meters per second to 0 for both days. So your change in velocity is constant. So, yeah. Now, notice that if you have a larger acceleration, you're going to be dividing by a larger number, so you have a smaller time. Likewise, if you have a smaller acceleration, right, your acceleration is smaller or your deceleration is smaller, it's going to take longer for the car to stop. And if it takes longer for the car to stop, let's say you've got a car moving and it takes longer, you have a longer time, then we know that distance is speed multiplied by time. Well, if you have a longer time, then you're going to have a longer distance, right? So the car is going to travel a larger distance or have a larger stopping distance. So from this, what we can now say is if you have a larger mass, if the mass of the car is larger, you're going to have a smaller acceleration, and therefore you're going to have a larger stopping distance. So that's the first thing. Now, I'm not going to do it for all of the factors that impact stopping distance, because the aim is just to finish the past paper. We could say that a larger mass will increase the stopping distance. We could say that a larger velocity will increase the stopping distance. We could say that if there's less friction, so a smaller force. And what could cause less friction? Well, maybe if the road, maybe it's like gravel instead of tarmac, for example, or like maybe it's wet because it's raining. So anything that might decrease the friction or increase the stopping distance. Also, the reaction time, if you have a longer reaction time, then it's going to take longer to react, so longer for you to press the brakes. So you're going to travel that extra distance before stopping. So these are all factors that might impact the stopping distance. Here, you just have to mention one. So I'm going to say, we're not going to talk about the mass of the car because, we're going to assume it's the same car and the same driver. So mass is not really relevant. We're not going to talk about the velocity either because the velocity is the same for both, right? 13 to 0. So instead, I'm going to talk about the other options. So I'm going to say a suggestion. It was raining that day. Explanation. This reduces the friction on the road. So there is a smaller average force. So there will be a smaller deceleration. Thus, it will take longer for the car to stop, and the car will travel a longer distance. Now, I obviously answered that as if it was a 4-mark question, and I added too much detail. But the main thing to say there will be a smaller acceleration, so it'll take longer for the car to stop. All right, let's carry on. So the figure shows a tumble dryer used to dry wet clothes. Hot air blows into the drum. So as you can see, the hot air, which gets heated, blows into the drum. The air gains water vapor. So the water vapor from the clothes, right? Because the clothes are wet. So it's going to pick up the water vapor. And then it leaves this section here. So it's took the water vapor. So now the air is more moist, right? More humid because it has the water vapor. And then it reaches this cold section here, this condenser. And we know that when, water vapor touches a cold surface, it condenses. So now all of the water is going to fall down. And then what's left is just the air. So the air goes up now, and then the air gets heated and it gets blown back. And then this process repeats itself until all of the water vapor gets condensed and all of your clothing is dry. All right. Hot air blows into the drum, the air gains water vapor. The moist air enters the condenser. Cool air leaves the condenser, passes through the heating element, enters the drum again. State the process by which the hot air removes water from the wet clothes. Well, the process where you remove water from anything, right, when water escapes the surface and leaves the surface, we call this evaporation. So we're going to say evaporation. Okay, the air is cooled as it passes through the condenser. As the air passes through the condenser, it's cooled. And it condenses. Describe and explain one other way in which the air leaving the condenser is different from the air entering the condenser. So yeah, the first thing is the air entering the condenser is hotter than the air leaving the condenser. But we need to state another way. Another thing is the air entering the condenser is very moist, is very humid. It has a lot of water vapor. Whereas the air leaving the condenser, it would have lost the water because the water condensed. So it's drier, it's less humid, less moist. So you could, however you want to phrase it, I'm going to say that the air is drier. And why? We're going to say because the water vapor has condensed. I don't know how to spell apparently. Condensed. There we go. The drum of the tumble dryer rotates, lifting up the wet clothes which fall down through the hot air. Name the force that causes the clothes to fall down. Well, the force that causes anything to fall down is the force of gravity, which we call weight, right? Weight is the force of gravity. That's the name of the force. And then when the drum rotates too fast, the clothes remain in contact with the wall of the drum. State the direction of the resultant force on the clothes during the circular motion. Well, this is called the centripetal force, right? The force for any object in circular motion, right? The force responsible for circular motion, we call it the centripetal force. And this is always acting at right angles. So it's always at right angles to the motion or to the velocity of the clothes. So I'll go back up to what I'm talking about. Where is it? So for example, when the clothes, let's say the clothes is stuck in this part of the dryer and it's as the drum's rotating, the clothes will be moving upwards. The force will be towards the center, right? It's always at right angles. And now when the clothes, which is this section here, and it's moving this direction, the force will also be at right angles, right? So you always have to say that the force is at right angles towards the center of, the circle. Okay, suggest why using a clothesline to dry clothes in the open air is better for the environment than using an electric tumble dryer. Well, the electric tumble dryer uses electricity, which burns fossil fuels, which produces greenhouse gases, not good for the environment. Whereas using open air you're using wind energy, and wind energy is renewable. So I would probably say something like a tumble dryer uses electricity. Which may involve burning fossil fuels, which can harm the environment, right? By producing greenhouse gases, for example. All right, let's carry on. So, a balloon of mass 15 grams, which is 0.015 kilograms, may have to convert. The straw is threaded onto a horizontal string shown. The balloon is filled with air and air is released. So you have a balloon, it's glued to some straw. And you guys could probably imagine that when the balloon is released and you allow the air to escape, you could imagine the balloon's going to fly in this direction here. All right, as the air leaves, the balloon experiences a force. The balloon accelerates from rest until it reaches a constant speed. It then travels a distance of 0.67 meters in 0.18 seconds at this constant speed. Explain in words what is meant by the term impulse. Impulse is referred to as the change in momentum. So impulse is the change in momentum, which is equal to, and you know the equation from impulse is force that is equal to the force or the average force exerted. So the force exerted, let's say average force, make it accurate, is equal to the average force multiplied by the time for which the force acts on, or the force acts. So yeah, we use this equation here, right? Impulse is equal to force multiplied by time. Keep in mind, impulse is also the same thing as change in momentum. But just because I wasn't sure what definition the mark scheme wanted, I kind of included both, right? I said that both impulse is the change in momentum of an object, but also impulse is the average force multiplied by the time the force is acting on the object for. So now 100% I'll get a mark. Calculate the resultant impulse on the balloon while it's accelerating. Okay, well, we know that impulse is either equal to force multiplied by time, or we know that impulse is the change in momentum. Thing is, I don't know how long the force was acting for, so I can't really use this equation. So, so instead, what I'm going to do is I'm going to use this equation here. Okay, I've been given the mass, right? The mass was 0.015. And now I have to multiply it by the change in velocity. So number impulse is basically the same thing as the mass times change in velocity, or change in mass times velocity. It's supposed to be the symbol delta for change. So the mass is 0.015. Now, what is the change in velocity? Well, the change in velocity is just the final velocity minus initial velocity. The initial velocity was 0 because it was moving from rest. My question is, what is the final velocity? That hasn't really given it to you. So there must be a way to work out this final velocity. Well, it's giving you that, it reaches a constant speed and it traveled this distance at this time. So it's giving you distance and time. And we know that speed is equal to the distance over time. So we could say that speed is a distance, which is 0.67 over the time, which is 0.18. This gives me the velocity. And now I could say that impulse is obviously mass times velocity. So mass times the velocity, which is 0.67 over 0.18. And this gives me sorry, my calculator stopped working. Just bear with me. This gives me this gave me 0.056 if I round to two decimal places or two significant figures. Now the unit for impulse, well, there's two units. If you used impulse as force times time, if we use this equation, we could deduce that one of the units for impulse is newtons multiplied by time, which is seconds, so Newton seconds. Or if we use the equation change in momentum, well, mass is kilograms and velocity is meters per second. So either kilograms meters per second or Newton seconds are both correct units for impulse. I'm just going to go with, I don't know, Newton seconds. Why not? So this will be my impulse. Explain how momentum is conserved as the ball accelerates. So we know the ball is going to accelerate in this direction. It's going to accelerate. But how is momentum conserved? Well, before you let go, the momentum of the ball was 0. So the initial momentum, its mass times velocity, was 0 because before the velocity was 0, it was at rest. So the momentum after must also be equal to 0. But how is that possible? Because the thing is, the balloon after had some momentum. It was moving to the right, right? So after the balloon was moving with some momentum, mass times velocity. But the momentum before was 0. So how can the momentum after also be 0 if it does have some positive momentum to the right-hand side? Well, the answer is when you let go, the air is forced out of the balloon. So the air that wasn't moving before is now moving, right? And it has some momentum to the left. So the air has some momentum. Let's call it m times v for the air. Now, the air has a momentum to the left, and the momentum of the air is equal to the momentum of the balloon plus the straw, right? Because it's both the balloon and the straw that's moving. So actually, the momentum is conserved because this minus this, right? The momentum of the balloon plus the air minus the momentum of the air that's leaving in opposite directions. If you add up these momentums, it will give you 0 because they're traveling in the opposite direction and have the same magnitude. So yeah, how would we phrase this? We would say, for example, the momentum before of the balloon and straw was 0. After the balloon was released, air. So how can I phrase this? The air released. Released has momentum equal in magnitude, but opposite in direction to the momentum of the balloon and straw. Therefore, and then we're going to say, therefore, the momentum after the balloon was released is also 0. So the momentum before was 0, the momentum after was 0. Why? Because the momentum of the air was equal and opposite in direction to the momentum of the balloon. So if you add up the momentum after, right, if you add this minus mv of the air to the plus mv of the balloon and straw, they just cancel each other out. All right. Figure 3.2 shows the directions of two forces acting on a balloon as it moves. Determine the magnitude. When your new syllabus, you only need to know the resultant force of, or resultant vectors for vectors at right angles. So this makes things really easy because we could always just use Pythagoras theorem. So what I'm going to do is the first step is you're going to have to draw it tip to tail. So I'm going to write this down. Step 1. Draw the vectors tip to tail. And step 2. And this is for the magnitude. You're going to have to use Pythagoras theorem. Wallah, I don't have to spell. Okay, and then step 3 is for the direction. You're just going to have to use tan inverse. We'll talk about all of these later. So let's just do step number 1. So I'm going to draw them tip to tail. So the tip of this vector has to touch the tail of the other vector. Because right now the tail's touching the tail. You can't really use this diagram. So I'm going to draw it again. I'm going to draw vectors. This is 0.4 newtons. And this is 0.74 newtons. Notice the tip is touching the tail. And the resultant vector is from where you started. Well, I started here and I ended here. So from the first tip towards the final tail, this is the resultant vector. And you know it's a right angle triangle, so we could use Pythagoras theorem such that a squared plus b squared is equal to c squared. And this is a, this is b, this is c. So we could say that c squared or c is equal to square root a squared plus b squared. So this resultant vector, c, is going to equal to square root 0.4 squared plus 0.74 squared. All right, so this will give me the magnitude. If I put this in my calculator, let me see what I get. I get 0. So we're going to say the magnitude is 0.84 newtons if I round. And then the direction, well, to work out the direction, it wants the direction relative to the horizontal force. Well, the horizontal force, if we have a look, is over here. So once the direction of the resultant force, this one over here, relative to the horizontal, right? So this is the resultant relative to the horizontal. He wants this angle here. Well, we're just going to use tan theta is equal to opposite over adjacent. The opposite, the side opposite the angle is 0.74, and the side adjacent to the angle is 0.4. So we could say that's equal to 0.74 over 0.4. And therefore, theta will equal to tan inverse 0.74 over 0.4. So that's what I meant by, if you want to work out a direction, you just use tan inverse. We're going to get 62 degrees to two significant figures. So we'll just write 62 degrees here. Okay, let's carry on. Figure 4.1 shows a bottle part filled with water. The air inside the bottle is at the same pressure as the air outside the bottle. So the pressure due to the air molecules inside It's just a quick recap. Why does, air produce a pressure inside a container? Well, the air molecules are moving randomly, and as they move randomly, they collide with the walls of the container. So there's a change in momentum, right? Let's say the air molecule is moving to the right and it collides with the wall, and then it rebounds, right? The momentum used to be mv, and now it's minus mv, right? So there's a change in momentum, and we know that force is equal to the change in momentum over the time of the collision. So that means it exerted a force because its momentum changed. Yeah, and because it exerted a force and pressure is force over area, there will be a pressure inside the container. Okay, it says the pressure inside the container is the same as the pressure outside the container. Likewise, there's also air molecules outside the container that are colliding, the momentum is changing, they exert a force. And it happens to be that these two pressures are balanced, they're the same. And that's why the bottle wouldn't get bigger or smaller. Okay, the temperature of the bottle and its content is increased. So you've increased the temperature of the bottle. So everything inside, right, you now have a higher temperature. It says explain in terms of particles, right? In terms of particles, how the air pressure inside the bottle changes as the temperature increases. So what I can say is as the temperature increases, the air molecules gain kinetic energy, right? Higher temperature, they have more kinetic energy. Or you could say, to be more accurate, it would be better to say the average kinetic energy of the air molecules or particles. It's more accurate to say molecules, but the question says explain in terms of particles. So I'm just going to use the word particles. The average kinetic energy of the particles increases. Okay. Now, because each particle has more kinetic energy, its speed will increase. Okay. So because your air molecules are now moving faster, they're going to end up colliding more frequently because they're moving faster. So you're going to have more frequent collisions. I'm going to write that down. So therefore, this will increase, or therefore there will be more frequent collisions between the air molecules and the walls of the container or the walls of the bottle. And also, because the molecules are moving faster, when they collide with the wall, they're going to collide with a larger speed. And if something hits you with a larger speed, it's going to exert a larger force. So we're going to say that not just there's more frequent collisions, furthermore, each collision will exert a larger force. Okay? So because there's more frequent collisions, so you're exerting a larger force. And because each force exerts a larger force, and we're going to say the volume remains constant. Why? Because the bottle is stiff. It's hard to stretch the bottle or compress it. So because the volume remains constant, we're going to say volume remains constant. And since pressure is equal to force over area, the pressure will increase. Why? Because as there is a larger force per unit area, as we use by the equation, there's a larger force per unit area, so there'll be a larger pressure. The lid is now removed. Stay and explain how the air pressure inside the bottle changes. Well, when you remove the lid, and the air pressure is inside is larger than the air pressure outside, what's going to happen is the molecules are going to want to escape, right? There's more pressure. Kind of like a perfume spray or deodorant. When you press the lid, you see the air rushing out, right? Because inside your perfume, your deodorant, there's a higher pressure than outside. So air is going to start leaving. Air will escape the bottle. Well, now you're going to have less air inside the bottle. Well, if you have less air inside the bottle, you're going to have less frequent collisions. So the pressure inside will start to reduce until you have the same pressure inside as you have outside, until the pressures, balance out. Then no more air will escape. Or maybe air escapes, but some more air enters. So the overall net flow of air is zero. So we're going to say the statement is the pressure will decrease. Why? The explanation will be as the air particles escape the bottle, so less frequent collisions inside the bottle, decreasing pressure. But I want to say the pressure will decrease, but on brackets I'll put it, until the pressure inside is equal to the pressure outside. So something like that. So the pressure will decrease until the pressure inside is equal to the pressure outside. Why? Because as the air particles escape, less blah blah. Okay, you guys get it. Let's move on. Calculate the thermal energy needed to increase the temperature, and it's giving you a specific heat capacity. This is obviously a specific heat capacity question. So we're going to start with the specific heat capacity equation, which is, the thermal energy is equal to M, which is the mass of your substance, multiplied by specific heat capacity of the substance, multiplied by the change in temperature. So let's just sub in the values. The mass is 0.18 kilograms. The specific heat capacity is 4,200. And your change in temperature is 20 because it increased by 20. So multiplied by 20. This gives us in standard form will be 1.5 times 10 to the 4. Don't forget a unit, which is joules. Another plastic bottle is filled to the top with water. The height of the bottle is 40 centimeters. The density is, so calculate the pressure difference between the top and the bottom of the water. Well, the change in pressure, right, underneath a liquid is equal to, and we know that the deeper down you go, let's say you have some liquid, the further down you go, the higher the pressure, right? And this change in pressure, how much the pressure increases by, is equal to the density of the liquid multiplied by the gravitational fluid strength, which is 9.8 in your new syllabus, and then multiplied by the depth, right? How much deeper you've gone, right? The change in height. So if we plug in these values, or density is 1 times 10 to the 3, G is 9.8, and the height is, well, the thing is the density was given in meters cubed. So I'm going to have to make sure the height is also given in meters. So 40 centimeters, 0.4 meters. And then this gives me if I put it in standard form, it will give me 3.9. I'm going to keep it in two significant figures just because this was given in two significant figures. So it's better to use the lowest number of significant figures given in the question, assuming it's not one significant figure. So 3.9 times 10 to the 1, 2, 3, 4, 5 pascals. Or if you want to use another unit, you could say newtons per meter squared. They're both correct units. And where did this unit come from? Well, this came from the equation pressure, force over area. The unit for force is newtons and the unit for area is meters squared. So newtons per meter squared, which is equivalent to the pascal. Okay, so question 5. All right. Figure 5.1 shows a road junction, a moving car, and a stationary truck. The road has high walls on each side. The driver of the truck is at position X. The car moves around the corner. On figure 5.1, label a point Y on the road where the truck driver first sees the car. Well, for him to see this car, then the light has to, a light ray has to go from the car towards him. And if the car is anything at a steeper angle than this, he won't be able to see it anymore. Why? Because the light will be blocked by the walls, right? So there has to be a clear straight line path from the car to the thing. So you'll probably just about see it when the car is somewhere in this position. So now I have to label it Y. The car is appearing to move like this. So we're just going to mark this point Y. Okay, now a plane mirror is placed at the road junction as shown. show how this mirror allows the driver off the truck to see the car. It's going to allow him to see it because the light can now reflect off the mirror now. So there will be a path for the light ray. So obviously the light has to reach the driver. So I'm just going to draw potentially light ray here in the mirror, and then they're going from the mirror to the driver. And then I'm going to draw the normal, because I have to check if the angle of incidence is equal to the angle of reflection. And yeah, it's roughly equal to. So yeah, this will be my, so make sure the normal is a dotted line. I'm not good at drawing, to be honest. Yeah, and obviously the light's going to hit the car, go from the car to the mirror, and then from the mirror back to his eyes so he could see it. Such that the angle of incidence is equal to the angle of reflection. The truck driver wears spectacles to correct long-sightedness. Figure 3.1 shows how a blurred image of object or form is. The reason it's blurred is because the light rays haven't met at the retina. For you to get a clear, sharp image, the light rays have to meet exactly on the retina. So wherever they're going, they have to meet on the retina. Here, they kind of don't manage to meet. So on figure 5.1, show how long-sightedness is corrected by adding a suitable lens. So in this case, to correct long-sightedness, you need to memorize that you want to use a converging lens. So a lens that looks like this, that's thicker in the middle. Okay, now what's going to happen to the light rays is when they reach this converging lens, they're going to refract a little bit first, right? Because that's what a convergent lens does, it refracts. And it converges, i.e. it gets closer together. So yeah, it's going to converge once. It's also going to converge a second time when it hits the second convergent lens inside the eye. And like so, you'd have corrected your long-sightedness. So what happened is some of the light rays hitting here, we've kind of made them hit here. So now there's enough room for them to refract and reach the retina. Okay. Figure shows circuit diagram for a flashlight. The EMF of the battery is 4.5. So your battery has an EMF of 4.5 volts. The circuit contains a 60 ohm fixed resistor. So this resistor has 60 ohms. And the current in the LED, so if I were to connect the ammeter next to it, the current in the series circuit is 0.02. That would be the same as the current everywhere else on the circuit because the current is the same in series. Calculate the potential difference across the LED. So you want to know what the voltage is on your LED. So what you can do is because we know the total voltage, the EMF, if we could work out the voltage here, we could work out what the voltage will be in the LED by using the voltage in series rules. Remember, the voltage in series rule is the following. It's the EMF is equal to the sum of your voltages. V2 plus V3 plus blah, blah, blah. Here we only have two things. So we can say the EMF is equal to the voltage across the 60 ohm resistor plus the voltage across your LED. We're trying to work out the voltage across the LED. So we could say that the voltage across the LED is equal to, I'm going to rearrange this equation, the EMF minus the voltage across your 60 ohm resistor. I know what the EMF is. The EMF is 4.5. And I can work out what the voltage is across the 60 ohm resistor because I know that voltage is current times resistance. And I know what the current is. The current is the same everywhere in series, is 0.02. And I know what the resistance is 60 ohms. So 60 times 0.2, I believe that gives me 1.2 ohms. So I mean 1.2 volts. So going back to this, the voltage across the LED is the EMF, which is 4.5 minus 1.2. This gives me 3.3 volts. Why? Because remember, the voltage of the EMF is equal to the sum of the voltages of your components in series. Now it says Explain why the LED does not light up if the battery is reserved. Well, the LED is a diode, right? And the diode only allows current, or the direction of the conventional current has to be in the same direction as the arrow. Otherwise, it won't flow through. So what I'm going to say is a LED is a type of diode, and diodes only allow current to flow through in one direction. Chemical energy stored is 1050 joules. Show that the flashlight operates for 3 hours. So it's giving you time and it's giving you energy. Sorry, it's giving you energy and it's asking for time. So the only equation that involves energy and time is the power equation. So we can say that power is equal to the energy transferred per unit time, right? That's the equation for power. But remember that power is the same thing as current times voltage, because it hasn't given you the power in the question, but it has given you the current and voltage. So current times voltage is equal to the energy over the time. Therefore, if I want to make time the subject, I could just switch these two around. So I could say time is equal to energy over the power, which is current times voltage. The energy is 1050. The current is the same everywhere. It's just 0.02. And the voltage is, in this case, will be the EMF, right? Of the circuit, total voltage, which was 4.5. Do this. You're going to get your time in seconds. So what do we get? Have a look. I get 11,666.6 seconds. But I want it in hours. So to go from seconds to minutes, I divide by 60. And then to go from minutes to hours, I divide by 60 again. So I just do the answer divided by 60 squared, or divided by 3,600. And then this gives me 3. So look, 11,666 divided by 60 squared. Gives me around 3.24 hours. I'll make sure you give more than 2 or 3 significant figures, because it's a show that question. You can't just say equals 3, right? Otherwise you haven't really showed it. So that's equal to 3.4, which obviously rounds, to around 3.3. Calculate total charge. Well, we know that charge is current times time. The current was 0.02 and the time is 3,600. Into your calculator it goes, and you get 72 coulombs. 72 coulombs, that's the unit for charge. Okay. Figure 7.1 shows some uses of electromagnetic radiation and different regions of the EM spectrum. Draw a line from each correct region, from each use to the correct region. So thermal imaging obviously uses infrared. Infrared's to do with heat. Photography, well, photo meaning light, right? You need visible light for any sort of photos. And then sterilizing medical equipment use gamma rays. You don't use ultraviolet because ultraviolet doesn't have enough energy to, kill all the pathogens in metals. Because sterilizing medical equipment usually involves really dense materials like metals. Okay. Say the speed of electromagnetic waves. Well, all EM waves have the speed of light, which is 3 × 10⁸ meters per second. Calculate the wavelength. Well, and it's giving you frequency. Well, we know that speed is equal to frequency times wavelength. And it says calculate the wavelength when the frequency is in the middle of the range. So this is the frequency range. The middle of this is 2.44 gigahertz. It wants the wavelength, so we're going to rearrange this equation. We're going to say wavelength is equal to speed over frequency. The speed is the speed of light, so 3 × 10⁸, because it's an electromagnetic wave. It's a Bluetooth headset, right? It uses radio waves. And sorry. Yeah, I was thinking of something else. I don't think it uses radio waves, because the frequency is too high. Well, either way, we know it's an electromagnetic wave that it uses. So the speed over the frequency, or we want the frequency in the middle, which is 2.44. It says gigahertz, giga meaning a billion, right? So times 10⁹. If I do this, you get 0.12 meters. Suggest why a Bluetooth headset only works well over short distances. We need to know that Bluetooth uses radio waves. This is part of your syllabus. So you're going to say Bluetooth uses radio waves, which lose energy, right, as they pass through walls. Or you could say the signal gets weaker as it passes through walls. So you're going to have a weak signal and you're not going to hear very well. Okay, question 8. The isotope of uranium-235 is represented by the following. Stay what the numbers 92 and 235 represent. Well, 92 is just the proton number, right? And then 235 is the nucleon number. So proton number and nucleon number. Nucleon number, how many protons and neutrons you have, right? All protons and neutrons are referred to as nucleons because they're part of the nucleus. Uranium-235 is a fuel used in nuclear reactors. Say the process by which energy is released from uranium-235. Well, this process is what we call nuclear fission, where uranium splits into two daughter nuclei or two or more neutrons and two or more neutrons, sorry, and energy is released in the process. Where did energy come from? Well, you've lost mass and mass was converted to energy. A nuclide equation for this process is following. Describe the mass and energy changes that take place during this process in a nuclear reactor. Well, what we could say is that, what can we say? Let me think. We could say that the nucleus of uranium is split to become what's become to Xe and Sr, which are more stable, right? So that's what's happening. However, the mass of the products is smaller than the mass of what you had at the start. What's that called? My English is not Englishing today. You have your products and you have your, the opposite of products, the constituents. Anyway, you get what I'm saying. The mass of the products is smaller than the mass of what we started with. This is because the mass has been converted into energy. So, or we could say that the change in mass or the loss in mass has been converted to energy. Now, what sort of energy is actually kinetic energy? Right, not thermal or anything, it's just kinetic energy. Okay, describe how thermal energy from nuclear reactions is used to generate electricity in a power station. Well, what we could say is, well, how do you produce electricity? It's generally you use heat to boil water, produce steam, and the steam spins a turbine, and that drives the generator. So we could say that the heat energy or this thermal energy is used to boil water and to produce steam. I want to say steam is moving at high speeds, pressures. This spins a turbine, which is connected to a generator. And we know what when the turbine and generator is moving, we could say there will be a change in magnetic field inducing an EMF. And that's how you basically produce electricity. Okay, say one advantage, one a disadvantage. Or advantage is that you could produce lots of energy. So for a small amount of fuel, so much energy is produced from uranium, from the fuel of nuclear fission. So you're going to say nuclear fission produces large amounts of energy for small amounts of fuel used up. Disadvantage is, well, uranium, although it releases a lot of energy, it's very rare or really expensive, or it could run out. Another difficulty could be that, the radiation produced, it's really expensive to get rid of the radiation. There's risks what if the nuclear power plant explodes, like what happened in Chernobyl. Any of these dangers are possible. But I think the biggest one is, well, nuclear power stations have like a lifespan, maybe 60 years or so, and then you have to decommission it and break it down. And these decommissioning costs, so decommission costs are really high for nuclear power plants. That's probably the main one. The table 9.1 shows information about 3 planets in the solar system. State the name of planet X. Well, planet X, if we have a look, it has a similar mass to the Earth. And also it's closer than the Earth, has a smaller average distance from the Earth. So it has to be between Mercury, Venus, and Mars. Now, from Mercury, Venus, and Mars, only Venus is like close to size than the Earth. The others are a lot smaller. It'll have to be Venus. Okay, describe the relationship shown in 9.1 between the mass and the gravitational field strength. Well, what we could conclude is the larger the mass, the larger the gravitational field strength, right? Gravity depends on the mass. Okay, explain why the distance is the average value. So here, the average distance from the sun. Why is that the average distance? That's because planets have elliptical orbits. They don't always have a fixed distance from the sun. So this is the sun, and here's a planet, for example. The orbit is elliptical. Sometimes it's close, other times it's, a bit further away. So that's why we talk about average distance instead, because the distance keeps changing. Show that average orbital speed. Well, orbital speed, we could say v is equal to 2 pi r over the time period. It's equivalent for orbital speed. So 2 pi r. So first of all, we need the radius of the Earth. Well, the Earth is giving me the radius of the orbit, sorry. It's giving you the average distance from the sun, which, the distance from the sun, the average distance from the sun is the same thing as the radius of the orbit. So that's what we're going to use. We're going to say, where's Earth? Earth is here. So 149.6, but it's 10 to the 6 kilometers. So what was the number? 149.6. 149.6 times 10 to the 6. I'm going to keep it in kilometers because it wants me to show that the average speed is in kilometers per second. That's why I didn't convert from kilometers to meters. Okay, now the time period, well, here's the orbital period, right? The time period is 365.2 days. So 365.2 days, but I want it in seconds because it wants the speed in kilometers per second. So to go from days to seconds, I know there's 24 hours in a day, and then 60 minutes in an hour, and 60 seconds in a minute. So times by 24, times by 60, times by 60. Put all of this onto your calculator, and you should get sorry, my calculator keeps doing this. 2 seconds. 2. Yeah, so I got 29.789 blah blah blah, which is around 30 kilometers a second. Okay, last question. So complete a sentences about the life cycle of a star. So protostars are formed from, well, you could say clouds of gas and dust, right? Clouds of gas and dust, or what we call nebula. It's called planetary nebula or stellar nebula, whatever. Okay, so a protostar becomes a stable star when something is balanced by, well, it's when the inward force of gravity. So gravity pushes the star inward. That's balanced by the outward force due to nuclear fusion. Right. So in a star, you have gravity pushing everything inwards, and then you also have fusion that releases energy, pushing everything outwards, and these are balanced. That's when a protostar becomes a stable main sequence star. The initial fuel used to power nuclear reaction in stars is, well, hydrogen, right? Hydrogen. into helium. That's the fuel. Stars that are approximately the same size of the sun become red giants, which then form a planetary nebula. That's that done, so I'm gonna have to end here. We ended anyway. I hope you enjoyed. Take care.